In our last lesson, we learned about reference counting, a simple approach to garbage collection. But reference counting has a fatal flaw. Imagine two objects that point to each other, creating a cycle. Object A holds a reference to B, and B holds a reference back to A. Even when your program no longer uses any object, their reference counts never drop to zero. They keep each other alive, creating a memory leak. This is the circular reference problem, and reference counting can't solve it. We need a different approach, one that asks a more fundamental question. Can the program actually reach this object? Mark and Sweep introduces a different approach called tracing garbage collection. Instead of counting how many references point to an object, we trace through memory to find which objects our program can actually access. Mark and Sweep executes in two distinct phases. Phase 1 is the mark phase, where we identify all objects the program can still reach. Phase 2 is the sweep phase, where we reclaim memory from all unmarked objects. Before we mark anything, we need starting points. Step 1, find the roots. Roots are the entrance points where the garbage collector begins its search. They include local variables on the stack, global variables in the program's data section, and values held in CPU registers. These are the only places where references can exist without being inside another object. We can understand the mark phase with a maze analogy. Think of the roots as the entrance to a maze. You start at the entrance, follow every path, and leave breadcrumbs as you go. When you're finished, any part of the maze with breadcrumbs is reachable from the entrance. Let's see the mark phase in action on a memory heap. We start at the root and begin tracing. Here are several objects on the heap labeled A through E. Our program's references create connections between objects. The root points to A and C. Object A points to B, and B points to E. Notice object D has no references pointing to it. The garbage collector begins tracing from the root. It follows the reference to A and marks it as reachable. From A, it follows the reference to B and marks it. Back at the root, it follows the second reference to C and marks it. From C, it follows the reference to E and marks it. All paths from the root have been explored. Object D remains unmarked because no chain of references from the root leads to it. This confirms D is unreachable and its memory can be reclaimed. Next comes the sweep phase. The collector scans through the whole heap, examining every object. For each object, it checks whether that object was marked during the trace. If the object is marked, we keep it and clear its mark for the next collection cycle. If it's not marked, we free its memory, making that space available for new allocations. Let's visualize the sweep phase in action. Here's our heap after the mark phase. Objects A, B, C, and E are marked with check marks. Objects D and F have no marks. The collector begins sweeping through memory. It scans and encounters unmarked object D. It frees D's memory, removing it from the heap. It continues scanning and encounters unmarked object F. It frees F's memory as well. The marked objects remain. The collector clears their marks to prepare for the next collection cycle. The sweep is complete. Mark and Sweep's biggest advantage is solving circular references. Consider objects A and B, where A holds a reference to B and B holds a reference back to A. With reference counting, these objects would never be collected because their counts never reach zero. But with mark and sweep, if there's no path from the roots to these objects, the tracing phase simply won't reach them. They remain unmarked during the mark phase. The sweep phase then frees both objects, preventing the memory leak. Mark and Sweep is widely used in practice. It's a foundation of the Java Virtual Machines garbage collector. The C# and .NET CLR use it. JavaScript's V8 engine builds on this algorithm. Mark and Sweep works well because it handles circular references correctly. It determines true reachability by tracing from the roots rather than counting references. This makes it reliable and robust for modern programming languages. Next, we'll discuss Mark Compact. Subscribe so you'll be notified when it's published.